So I'm going to talk about RMG Cat, which was what we originally called RMG for Catalysis. And for a while, it was a separate fork, and you had to install it separately. It was different enough that we gave it a different name. And then we've managed to merge it back into the main branch after a Herculean effort, largely by Emily Mazau. And it was, yeah, it's now just in RMG. So RMG is RMG Cat. We still have an RMG Cat Slack channel and a sticker on my mug with a cat on it and stuff, but it is now just RMG. Main developers and contributors. So it was Franklin and myself that did the first fork and got RMG to work for Catalysis. For a while, it was like once a week, we would just open Zoom and do pair coding remotely. He was in Providence, I was often in Connecticut, and we would just spend an afternoon a week just kind of hacking at this, trying to get it to work until it was working. Bjarne Kreitz was Franklin's postdoc, is now an assistant professor at Georgia Tech. And he's done a huge amount of work and is helping a lot with it now as well. Other people who've contributed, Chris and Chow were my PhD students. Sevi is still my PhD student. Kirk is in the room too. He is Franklin's PhD student. And Matt, who you just heard from, is now at San Diego National Lab working on catalysis. While he was here in the green group, he wasn't doing catalysis, but he's now doing a postdoc at San Diego and is helping with the catalysis side of things. So these are the main contributors, but probably not the only ones. So apologies if your picture is not here yet. So introduction. So heterogeneous catalysis is essential in many industrial processes. I wanted the numbers like 80% of everything that we use is touched a catalyst in its life or something. And in fact, something is like 80% of us, like or 90% of the nitrogen in your body touched a catalyst before it ended up in a fertilizer and then in a plant and then in an animal and then in you. So catalysts are important. Typically, heterogeneous catalysts are solids reacting with liquids or gases. And so they're things like platinum in your catalytic converter on your car or all sorts of things. RMG can now model gas surface systems on simple metals. So that's where we're at. We can do gas phase molecules with carbon, hydrogen, oxygen, to some extent nitrogen. Kirk is working hard at that. Single terrace sites, for example, platinum 111 facet. So for those of you not metallurgists, that defines your crystal structure and the plane of your surface. And we can couple the gas phase and the surface reactions. So all of the RMG reaction families can be happening in the gas phase and they're coupled with the ones on the surface. So catalytic combustion, where it's ignited by the platinum, but then burns in the gas phase. All of that is taken care of. Some examples that we've applied it to: catalytic partial oxidation of methane. So you've got methane and you want to partially burn it to make CO, but not all the way to CO2. Steam reforming of methane, CO2 methanation, oxidation of hydrocarbons, alkyne dehydrogenation, a few of these things. Some things we're still working towards, like Fischer-Tropsch or whatever, molecular weight growth, all sorts of things that we're working towards, but these we've already done. Okay, so we represent surface species the same way as gas phase species with these adjacency lists that I spoke about yesterday. So this is methanol as an adjacency list for methanol. And then this would be, if you replace this H with the surface, you replace it with an X. So the surface site is an X. And here we can see that there's a single bond to atom 2, which is the O. And so we'd see it. So it just shows with an X in the adjacency list. We can now represent all sorts of adsorbates. So we can do monodentate adsorbates. So this is CH triple bonded to the surface to X. So we've got a triple bond T. We can do fizz-adsorbed species where there is no bond. It's just van der Waals interactions that's just holding it loosely on the surface. So this is H2, so that H atoms are bonded to each other, and the X is just there with no bond. We can do bidentate or multidentate things where the two different atoms are both bonded to the surface. So here you've got two different X sites, and we can see one of them is single bonded to atom 1, and one of them is double bonded to atom 2. So we can do this. Maybe we mention it later, but the resonance forms of this type of thing where you can have, like, is this the double bond and that the single or whatever, is something that's recently gotten much better, but probably there's still progress to make there. X atom types. So X is a surface site, and in a molecule, you just use X. But when you're talking about a functional group definition, you might want to have X vacant and X occupied to be different atom types. And in the SMILE string, it's often drawn as a platinum, or less now a nickel. But and you can input, when doing SMILE's input, I think you can use an asterisk. That's about all there is to say for that. So yes, when you're doing a reaction family template, you might want to say that it's an XV for vacant if you're doing like an adsorption reaction or something. Van der Waals bonds I just mentioned, but yeah, so in an adjacency list, it's done with the absence of a bond. So I just got X with no bond, as I talked about. When you're in a reaction recipe, you want to say, okay, this adsorbs to the surface. You form a bond of order 0. So in a reaction recipe, you're making a bond with bond order 0. Temporarily, H bonds were 0, but they're now 0.1. So a hydrogen bond between like an H and an OH inside something is 0.1, and a Van der Waals bond is 0. And then after it has applied this reaction recipe and formed a bond of order 0, it'll delete the bond and turn it back into this species representation. Okay, the thermochemistry of the adsorbates. The way we estimate this, well, the first thing we do is look it up in a database. If we've got a number for methyl on platinum, we'll use it, right? We'll check the database first. If we have to estimate it, we estimate the methyl, and that probably we'll find in a database. But if we don't have that, we'll estimate that using all the methods we learned yesterday. And then we figure out how does that change when we stick it on the surface. And so we've got these trees. They're very much like the group additive trees or the subgraph isomorphic trees that we've seen several times. They're all over the place in RMG. And we've got one for the adsorption correction. So it's going to tell you how does the enthalpy and entropy and heat capacity change when you bring something and stick it on platinum 111. The data for this was all derived from bespoke DFT calculations, many of them done by Katrin, who was a student in Franklin's group, but many have been updated since by Bjarne or Kirk. And there's about 160 adsorbates. This is just showing the carbon tree, but there's another one for oxygen, hydrogen, nitrogen. And so it just like other hierarchical trees, you start off with, in this case, carbon. You say, well, is it a single bond, a double bond, etc. And then you can get more and more specific. And so there's lots of examples for each. So sometimes for the CH2, there might be several different examples we've used. But that's just for platinum 111. We want RMG cat, not RMG platinum. So we then had to get to other metals. So we rely on, for now, linear scaling relations. It was discovered, published by Abel Peterson in 2007. I don't know if he actually discovered it, but this is the paper everyone cites, showing that if you change metal, so you adsorb CH2 on metal, on platinum here, and then you adsorb it on a bunch of different metals, and you calculate all of these adsorption energies using DFT, you find that this adsorption energy of CH2 scales linearly with the adsorption energy of a carbon atom. And furthermore, the slope of this line is a half, or 0.49. The slope of this line, which was for CH3, is a quarter. The slope of this line, which is for CH, is 0.75, 3/4. So he realized that 3 lines here, and the slope is 3/4. 2 lines here, the slope is 2/4. 1 line here, the slope is 1/4. And so you can guess the slope of the line based on the number of bonds to the surface. And that means that you can get, if you know platinum, you can guess any metal. So that's kind of how we do it. The next couple of slides illustrate that. This slide shows that it works for nitrogen as well, that this is 1/3 or 2/3. It works for oxygen, it's 1/2 or 1, and even sulfur. So it seems to work for many. You'll notice that there is still quite a lot of scatter, right? You're only going to be within like 0.3 electron volts using this method. But then your DFT is only 0.3 electron volts anyway. So you're only adding on, you're only doubling your error from doing a DFT calculation. So yeah, the concept is if going from platinum to nickel for a carbon atom is 0.32 electron volts different, then this is going to be 1/4 of that because you've got one line here instead of 4. And so that means that we can do anything on any metal. So on oxygen, if going from platinum to nickel costs you 1.2 electron volts, then for this, it's going to be half that because you've got one line instead of 2. Any questions? All right. Yes. Question from Marcus. Just speak into it.
I have no idea where the microphone is. Okay, so the question is, in catalysis,
Yeah.
the bomb, the atom where the bomb goes to is not the only influence of the bond and what happens above. So the neighbors, and in particular the geometry, you know,
right.
it's an edge bond or whether it's a, you know, a corner atom.
Right. I keep drawing these going to the atom, but in fact it's often a bridging site or a hollow or a well or whatever.
Or just,
right. I keep drawing these as atops, right?
So the local structure.
Yeah.
It's important.
This represents a surface site, and we use the preferable surface site. So this, in fact, might be bridged between the two platinums, or between 3 platinums or 4 or whatever, and it always represents the favored surface site. And that might be why there's so much scatter on these plots, that type of thing. You're right. This is a gross cartoon to say that it always sticks directly to the platinum.
But whether it's it's an H.
Yeah. Exactly. Yeah. So the platinum 111 is going to be different from 110, and it's going to be different from it's like most philosophy in RMG. It's like some guess is better than no guess, even though it's an approximation. Another question. Yeah.
And my question goes in the same direction. So currently you're only evaluating the platinum 111, so the other surface sites are not yet included, or the 110 or something.
Right. For now.
For now. And maybe to make it much more complicated, precious metal catalysts are often supported on different supports. And the support, if it's alumina or it's titania or silicon carbide or stuff like that, has also some effect on reactivity and selectivity.
Yes.
Are there any ideas or concepts how to take that into account?
In the interest of time, I'll just say no and move on. All ideas welcome. So yeah, if it's not in the database, we estimate the gas phase first of all. We add on these corrections, and then we change the binding energy with the linear scaling relation. So this is the kind of graphical flow diagram of how we can now get any adsorbate on quote any metal. What's so special about platinum? Why platinum 111? The very first proof of concept we used nickel. Then we switched to using platinum as our reference one. And it's just that's the first database that we did a lot of uniform calculations so that they're all analogous. And it's the main thing in all chemistry is always deltas in energy, and so we wanted to have something uniform where we did all of the calculations ourselves, all on the same facet, all on the same metal, So the reaction energies end up right. Not to say you couldn't do the entire tree again on something else. And in fact, we have efforts that are doing that. Like with electrochemistry, we're doing a whole ton on copper, and maybe, do you aware of any other whole trees? Okay. But to do the linear scaling, you can in your input file either specify the binding energies of carbon, nitrogen, oxygen, hydrogen, or some of them are looked in a database, and you can just say, I want to scale to gold or rhodium or whatever, and it's already got them in a database. So how do you that's on this one? You can either specify scale it to a certain metal, or you can say scale it to this hypothetical metal. My group often does screening studies where we'll do a whole array of like many hypothetical metals. We don't even know what there is, but if there was a metal with these binding energies, how would it behave? Some tips for constructing the surface input files. Restricting your number of species to a certain number of surface sites. Just like you had maximum carbon atoms we heard about, you can set maximum sites. 2 is a good idea. It'll predict the existence of things with 3, 4, 5, but our estimates of the binding is going to get worse and worse and worse. And similarly, restrict your model size if you want vaguely reliable numbers. Reaction kinetics. So we have reaction families, just like we learned about in the gas phase. There's different types of adsorption. We started off with just dissociative adsorption, so H2 can split into 2 H atoms when it sticks. Non-dissociative adsorption, so CH3 could just stick on its own. Dissociation, CH3 could split into CH2 and H. Abstraction, you could have something takes one from an adjacent. We found that published mechanisms seldom include these abstraction reactions, and RMG built mechanisms have a whole ton of them. So certainly they can exist, or RMG will hypothesize. If you tell RMG the existence of this family, it will find that template matches a whole ton of stuff. We now added many new families. So there's illyridial chemistry, where something from the gas phase reacts directly with something on the surface. And some van der Waals families, where things that are fizz-adsorbed to the surface react. And other types of recombination reactions and migration, where things can change which atom is causing the binding. So there's a lot more families are now on, and we're still adding more. These are all grouped together in there's the file called recommended that's in the kinetics database, has them grouped together, so you can say I want the set called surface as well as the set called default, which default is the gas phase thing. So you turn on the kinetics families here, or you can turn them on individually or turn them on and off as you choose. Yes, another question.
When you when you solve this system, do you treat the surface atom as a species, just like any other species? I mean, like obviously, I mean,
in a differential, maybe I'll answer that in a second, I think.
okay.
What was I meant to finish in 20 minutes? Am I like already over time?
Matt went over 15, so if you just
how late are we behind schedule?
it's not so important.
Okay. Okay, so the rates, first of all, look in a database if it's there. If not, we're going to estimate it similar way to the other things with the families and the trees. There's more Bell-Evans-Polanyi relations in the families because there's less kinetic training data on the surface than in the gas phase chemistry. So there's a greater reliance on linear estimates because many of our trees are just pretty barren, not many leaves on the trees at the moment. The surface reaction types, surface areneous is very much like Arrhenius, but with different units because it's now per square centimeter, because it depends on or per surface site. The sticking coefficient is again a bit like Arrhenius, but it's a number between 0 and 1, which represents what fraction of collisions with the surface will stick. And so it's then combined with this expression, which is how often will something collide with the surface. So this is based on basically the average velocity of a particle in the direction of the surface is going to say how often it will stick, how often it will hit the surface. And then S is how likely it is to stick, which follows kind of an Arrhenius expression, but bound between 0 and 1. Coverage-dependent kinetics. And now coverage-dependent thermodynamics. It turns out that just like we learned about pressure dependence, where things that aren't actually reacting with you can still affect your rate through collisions or whatever, on a surface, things that you're not directly reacting with can affect your rate just because they're nearby. And they're nearby you on the surface, they influence you. And so you need often expressions to change the rate constants based on the coverage of other things. And so there's a few standardized parameterized ways to do that in the literature that are in ChemKit and Cantera and so on. And RMG can now read those from libraries, use them in its simulations, and write them in its results, but it doesn't yet estimate them. So it will kind of respect them if you've told it, here's the pressure dependent, the coverage dependence. It will use that in its simulations and it will spit it out in the Chemkin file, but it can't guess them yet. But you have to turn it on with coverage dependence equals true, and make sure that you've got some coverage dependent libraries. The reactors, this is a little bit what Marcus was asking about. A surface reactor, it's a constant volume isothermal batch reactor, pretty much like the simple reactor in RMG, but with a surface which has to have a surface site density, which is how many sites per square centimeter there are. You've then also got to specify the surface area to volume ratio, which basically tracks how much catalyst is in your related to the gas phase. And then we solve it in terms of number of moles, not mole fractions. So we're counting number of vacant sites. So at the beginning, we calculate how many sites are in this box of gas, and then convert all the rates onto a per volume basis and solve the differential equations are solved on number of moles of site, vacant site, or stuff. Now I know that RMS can do surface reactions, but I think that the RMS surface reactors are not accessible inside RMG. So I think in RMG it's not using RMS surface reactors, just this inbuilt simple one. You can do sampling over temperature, so you can set a temperature range and it will sample across that range, like we heard about yesterday, but you can't yet sample over pressure as well. You set the surface coverages as well as the initial mole fractions for the gas, and you have to specify the surface area to volume ratio. Now you can create multiple surface reactors in your input file, of course. So if you think that some of these parameters you're not sure about, or you think they might matter, or you're not sure if they matter, you can create multiple input files, multiple reactors in your input file. As we've heard many examples that RMG is just part of an iterative process. Use it as a collaborator to suggest reaction mechanisms, and then go and calculate them, simulate them, see if they make sense, do sensitivity, do degree of rate control, calculate the ones that matter, update your databases, and run RMG again. If you just tell RMG to build you a catalytic mechanism, it's going to be even worse than a gas phase one. But it's just already a very helpful tool as part of this workflow. Over the last several years now, it's catching on. Most of these papers are by us, but they're getting accepted. And so it's been used and it's growing and it's more useful by the day. It's particularly promising with a combination with uncertainty quantification. This is philosophically a little touchy because I grew up as a Bill Green disciple thinking that fitting was an ugly word. And he's absolutely right. But yeah, the parameters ab initio for catalysis are so bad that you'll never get it right predictively. If you just say, okay, I'm going to rely on linear scaling and DFT and whatever. And so all you can ever conclude is that you were wrong, which is, so we say, okay, well, if we say there was a lot of uncertainty in all these parameters, could I have been right? Is there a right answer in here somewhere? We find that there's promise to that approach. And so we got a couple of examples. Bjarne did one where he's like, okay, I'm going to look at the correlated uncertainties between a whole ton of I know that all of these parameters are uncertain, but assume that they deal with the correlations correctly and find, is there a good answer in there somewhere? My students did another version that's similar, but they were comparing different ways of estimating the parameters, whether it was actually DFT calculations or using these linear scaling approximations, or there's some machine learned potentials that are like way faster than DFT, but trained on it. And they found that yes, the uncertainties, the prior uncertainties are different, but if you do Bayesian parameter estimation, you end up with similar posterior uncertainties. And so we think that there's promise in using that kind of approach. Still lots of open challenges. Lack of data is the main one. DFT is not even very accurate. So even if you had exascale computers, which we now are part of a team using exascale computers, so we kind of, as soon as it's possible to calculate these things on the world's fastest computer, we're first in line to do it. But even then, it's not very accurate. There's no site specificity. Linear scaling doesn't work for anything. We can only do metals, not oxides or zeolites or supports or all sorts. Coverage dependence we're still working towards. Adsorbed formate, it's hard. There are these bidentate resonance forms, etc. Things are complicated. There's lots to do. We're at it. We're working towards coverage-dependent thermodynamics. Resonance for adsorbates. Some of these are open pull requests that are nearly done. And some of them are more kind of, that would be nice in the future ideas. Should acknowledge Northeastern and Brown, Department of Energy, Exascale Computational Catalysis Project, various other stuff. Any questions?
So is there pressure dependence in this? Or if there's a very exothermic surface reactions, does it distribute the energy to the surface or
No.
that's with bath gas collisions?
No. I don't know if you could turn PDEP on and catalysis at the same time. I don't even know if you could treat the gas phase with PDEP while having catalysis.
Is there any experimental evidence of pressure dependence?
Pass. You mean all the stuff my previous talk about pressure dependence? Is that what you're referring to?
Yeah, pressure dependent kinetics.
I don't know. Have to think about it.
Well, you had to specify the pressure, but was that only for the mole fractions?
Yeah, so there's pressure in the gas phase. It's interacting with the surface and reacting with the surface. And so you could have pressure-dependent chemistry. I mean, you can have like catalytic combustion, right? You could have pressure-dependent reactions in the gas phase. And some of those species are absorbing onto the surface. But I think that the rates on the surface would not be pressure-dependent so much as, yeah.
Okay.
Yeah, hello, good evening. Can you hear me?
Yep. Yes, we can.
Okay, yeah, thank you for the lecture. So I need a clarification regarding this RMG cards. So and sometimes is it like a year back? So I attempt using it to simulate a catalytic process that was non-oxidative. So I raised it earlier in one of the lectures during this program. So I said I'm going to raise it up again. So because like it's not all reactions that are really oxidative. So and there are some really, especially like non-oxidative. Let's say like one of the examples you cited, which was propane, the alkane dehydrogenation. There are some oxidative and non-oxidative process that is used in carrying out that. So especially if you're interested in non-oxidative dehydrogenation of the alkanes, so certainly you should not be one of the product or byproduct or side reaction product you expect. So it should not be like oxygen-based compound. So finding something like this in the product, certainly I know me today, because like that period I was attempting to do that. So, and without allowing that to like generate oxygen-based compound, it was making the simulation impossible. So I don't know, maybe if now you can simulate that kind of scenario without engaging the oxygen part of the catalyst or the system that have been like designed to, because I know that the group have been working on a lot on combustion related or pyrolysis kind of thing. So sometimes which cannot do without the oxygen.
I don't see a reason why it would fail if you didn't put oxygen in the system. It should have enough reaction families that something will happen and it will discover the chemistry that can occur. If you run a simulation with no oxygen or insufficient oxygen, it should discover the pathways that occur non-oxidatively. Anyone else who's Catalysis have thoughts?
Maybe because of the short time that we have for the workshop, so maybe after the workshop, I'm going to repeat the same story and share my feedback, because as of then, when I did the test, really because we want to do something different, but we just say, okay, let's first test this simple case with the app. So, and we had this challenge. So, which we did, because without like playing with the part that has inclusion of the oxygen, so the simulation was not working. And when we allow the oxygen to take part, it's generating product that we are not anticipating.
Okay. So issue on the issue tracker with some details of what you expect to occur and what is occurring, and someone will hopefully have a chance to look at it. Reach out to us. Yeah. I mean, I can't think of a limitation of why it shouldn't work. So something must be unexpected. So yeah, I'd suggest that. We'd be happy to help.
All right. I'll keep you updated of the test when I do that after the workshop. Thank you.
Okay. I think we could just keep going with Matt's last half hour talk.
Yeah, so we originally had a break scheduled, but
So fill up your coffee cups if you want.
maybe we can take like a 1 minute break.
Yeah, like a 1 or 2
minute break.
And I have a comment regarding this. I know at the moment the code is designed to deal with pure metals. So, but in a case like you were saying, I don't know how much we can rely on doing that. That's using relative values to model non-pure metal catalysts like the metalloid, what they call metal oxide or zeolite kind of catalyst.
If you can update the database, whether it's the general trees so that it can estimate everything, or specific values that you know, then you can model anything. As long as you can represent surface site with an X, then you're fine. It just becomes a parameter estimation problem. The restrictions are, at the moment, you can only do one type of surface site X. the ability to say, well, I've got different types of surface site all at once is something we're working towards, but doesn't exist yet. But otherwise, it's just a question of estimating the parameters. So if you have a way to estimate the parameters, then you should be able to model anything. But
and in addition, can you share maybe at the end of the workshop, maybe maybe a paper or reference material used for estimating the parameter for the platinum that is currently being used, so that can be used as a reference for coming up with one that is non-metal.
okay, I'll put it in the Zoom chat, I think.
All right, thank you very much.